Hello and welcome back. So moving on, so far we've seen some introduction to supervised and unsupervised machine learning, basic terminology in machine learning, the idea of tasks, and just the different tasks in supervised and unsupervised machine learning. We've discussed in some more details different probabilistic models and generative models that can be used either to generate data or to do other kinds of tasks like dimension reduction and clustering. So in this next section, we'll take a slightly deeper dive into the concept of generative models in general and what they are, what they mean, how they relate to nonlinear mixed effects modeling, if you're familiar with that concept or that field. Basically, the two are very, very connected and in fact can be argued to be the exact same thing. And there's a webinar on the YouTube channel of DeepPumas AI that basically walks through some of the same concepts we're going to be explaining now, but we'll try to be a bit more brief in this slide deck. Or maybe not, we'll see. So the goal of generative models in general is to try and generate synthetic data that is indistinguishable in distribution from the real data. So what that means is, for example, if we have some normal distribution, let's say these lines here are the contours of the log PDF or the log probability density function of a normal distribution. So normal distribution would be centered around this middle here, and then it would basically, you'd have less and less values as you go away from the center. And all the values on the contour, on one of these contours, have the same log probability density function. So they should all be equally probable, essentially. And this looks like, again, a multivariate normal distribution, or this is a multivariate normal distribution. Now, let's say that we have observed some data, so all the blue points are observations, and then we fitted to this data, we hypothesized that this data comes from a multivariate Gaussian. And then we can fit the Gaussian, or we fitted the Gaussian to this data. We got some mean and some covariance matrix, and this is what the plot here is essentially. These are the contour plots of the log PDF of the fitted Gaussian to the blue points. Now the hope is that with generative models, or if we did a good job figuring out a generative model that fits our data, is that when we simulate from this model, when we generate new samples from this model, synthetic data essentially, which are all the red points here, that then we won't be able to tell them apart from each other in distribution. So maybe obviously the individual points will still be different, but if you look at roughly the distribution of blue points and roughly the distribution of the red points, for a large enough sample, you should not be able to tell any significant differences between the two distributions. Now, this can apply to points, or it can apply to much higher dimensional data, such as photos or images with many pixels, for example. So there is actually a website that's dedicated to generating, or it's based on a generative model that was learned or fitted to a whole number of, like a very large number of photos of actual people. And then the idea is that it's then able to actually generate some random people that don't even exist. And just because it learns roughly what the distribution of faces should look like. Now, there might be a person out there who looks similar to this guy, but there's probably no one person out there who looks exactly the same as this person here, pixel for pixel. So it is still very much similar to this, where the individual points, they're similar, but they're not the exact same points, right? So the generated points are still basically largely novel or new or imagined points, if you like. Just like these faces here are imagined faces of individuals and not real faces, although I'm sure there will be people out there who look similar to these people. And again, you can do this with images, or in our case, for example, in pharmacometrics, we often have to do this with longitudinal data or time series data or panel data. And so let's say that we have some clinical trial data, and for this clinical trial we have multiple individuals. Each of these curves here represents an individual. So if we focus on just one person or one individual, we have multiple observations over time. So this could be some drug concentration, some tumor size, any kind of pharmacodynamic variable that we care about. And we basically measure it over time, multiple times, and for every patient we have a different trajectory. Now, one thing we're often interested in doing is actually learning the distribution of this longitudinal data. So I would like to learn or have a generative model that's then able to actually simulate data that looks like the real data. And the common check that we use for this is something called a visual predictive check. Now, if you think about it, two distributions are identical if they have the same, two univariate distributions are identical if they have the same quantiles. So the first quantile or the first percentile of the first distribution should match the first percentile of the second distribution, second percentile should match the second, third percentile should match the third. And so ideally, if two distributions are identical, their percentiles, the respective percentiles, should all match each other. And the VPC is sort of a simple check for just 3 of those percentiles. So often it would be like the 5th percentile, the 50th, and the 95th. And the idea is that we want to make sure that the observed distribution quantiles or percentiles match the simulated distribution percentiles. And so the observed percentiles or quantiles here would be represented by the black line, and then essentially we do multiple simulations, and then we get different quantiles every time, and we plot some interval, essentially some prediction interval around what the percentile looks like, or the simulated percentiles are, and then the hope is that this band here will include the observed quantile, and the blue line is essentially the median within the band, so it's the median of that band here. But again, largely at a very high conceptual level, what the VPC is trying to check, or this visual predictive check is trying to actually check, is the mismatch. So any potential mismatch between these 3 percentiles, or in these 3 percentiles between the observed data distribution and the simulated data distribution. And so imagine, for example, this person here had like 2 noses. Then that would be a very clear discrepancy from the distribution of faces that we are familiar with. And with images, maybe it's easy to just look at it and tell, okay, this falls within the distribution or not. Right? If you're able to recognize or to tell that this is a fake image very, very clearly, then perhaps it's actually out of the distribution, or it doesn't actually match the real observations. Whereas maybe with time series data, it can be a little bit more tricky, but the visual predictive check is essentially trying to automate or to do something like very, very similar, which is if the observed percentiles are outside the simulated percentiles, then we can conclude that the 2 distributions do not match one another. Now, just because these 3 percentiles match doesn't actually guarantee that the 2 distributions are identical, because there could be other percentiles that don't match. Right? So this is more of a check for the dissimilarity of the 2 distributions, but if the VPC looks good, it doesn't actually tell us that this is a perfect model. It just tells us that for these 3 quantiles, we're not able to prove that this is a bad model, right? So we have to be slightly nuanced there. So it is more of a like a bad VPC tells us something about the model, but a good VPC doesn't necessarily confirm that this is a good model, although that's how most people would normally interpret it. But that's, again, conceptually what the goal of a visual predictive check is, and that's generally the goal of generative models, is to learn the distribution of data, and then you can hopefully simulate from that model so that you can generate data that looks like the real data. And that applies across points in the Euclidean space, across images with many pixels, or across time series data and longitudinal data. Now, let's talk a little bit more about the data structure that we often have to work with in pharmacometrics. Now, probably all of us here are familiar with some of these concepts, but let's just introduce them anyways, because they're going to be quite useful in the discussions. So as we all know, the data that we work with, for example, if it's clinical trial data, is often hierarchical in nature. So what that means is that we have, for example, multiple subjects in a population. For each subject, we probably have multiple different variables that we're measuring, like drug concentration and maybe some other measurement like tumor size and maybe survival. And then within each of those variables, we often have multiple measurements. So we might have multiple drug concentration measurements and multiple tumor size measurements and so on. Obviously, we can only have one survival measurement, or it can be censored. And then the data is often heterogeneous. So that means, for example, the number of points that we get from our PK or pharmacokinetic observation or variable is often different from the number of observations we have for the PD or for the pharmacodynamic variable. And we could have, for example, a different number of measurements for drug concentration versus tumor size versus survival, even though we have all three for the individual. And that's so there's sort of this heterogeneity within the subject, but also there are between subject variability or heterogeneity where I might have just 3 observations for one subject and maybe 5 observations for another subject, because maybe the first subject dropped out early from the trial or was taken off the trial because the drug was seen to not be very efficacious or useful for that patient. And so it's possible that I might have a lot more observations for one subject compared to the other. So the data has this hierarchical nature, but also has this sort of heterogeneous nature that makes it sometimes or slightly more challenging to work with compared to very simple sort of tabular data. Now, the data is longitudinal. As we said, each subject has one or more responses or what response variables, for example, PK and PD, maybe survival or time to event data. Every response variable can have one or more observations, and response variables can have a different number of observations either across or within the subject. So that's the same points that we just mentioned. Now, compare this or contrast this to images or scan data. So imagine we have actually an image. Not a generated image, but a real image that's observed for a specific subject. Now, every subject can have one or more images or scans. So in the medical context, that could be like a CT scan or an MRI scan. And in computer vision, that could be the photo of the person or a video of the person doing something. And so every subject can essentially have one or more such images or scans. Now, every image or scan has many pixels or points, but each image and scan, again, can have different number of pixels, meaning that the CT scan, for example, may have a very different representation compared to the MRI scan. But also, for the same patient, if you take a CT scan or an MRI scan, you might have slightly different resolution, you might have slightly different quality of the scan depending on the operator, for example, of the machine. And so you might have slightly different also representations even for the same scan between different subjects. And so once again, it's very similar to the case of longitudinal data where we have one or more essentially variables, but the variable in this case is a full image or a full scan. And the variable itself has multiple observations. In this case, the observations are not just observations over time, but they're essentially observations over space, where we have different pixels and different points in space, right? But it's the same concept here. It's over time, different variables over time, or different measurements over time, and here's different measurements over the spatial sort of context. And once again, images can have different sizes and resolutions and so on, either within subjects or across subjects. And so we have this, once again, hierarchy in nature or heterogeneity in nature. And I'm sort of drawing also the analogy here between longitudinal data, which we're much more familiar with, and between something like image or scan data. Now, we could also have longitudinal image data or longitudinal scan data, where we might take a scan across different points in time. And so that would add sort of another level of hierarchy, where we could have obviously the multiple time points where we have scans, and then within each scan we have many pixels or point cloud representations of the scan. And so this could also be sort of, these could be combined together to form one more level of hierarchy. Good. So the key point and why we should care about the data structure is that because we're trying to generate data that looks like the real data, we need to make sure that our data that's generated has the same structure as the real data. And that necessarily means that the models need to also respect this structure or be sort of crafted such that they have the same structure for the data output. And so, for example, we would use or we would normally use temporal models or models that are function, like that use time essentially for modeling time series data. We would use spatial models for image and scan or spatial data, where spatial here just means that we have multiple data points across different obviously points in space, but there's also meaning there's neighborhood information. So we have this idea that there some points might be next to each other, other points are further away from each other, and it's not just along one dimension like in time, but it's along multiple dimensions. And that kind of structure can be actually baked into the model essentially, or the models need to respect that structure. So that brings us to the idea or to model structure in general. Now, for simplicity, we're going to be talking about a very simple context where basically we care more about we will look first just at these sort of points here. So just assuming that our data is just a bunch of two-dimensional points in space. Nothing else. Now, you could intuitively think of these as two different measurements that you care about, but just for mathematical purposes, we will assume that our data has this form here, although the same math and logic that we will see largely applies also to other contexts, and we'll see how to generalize it in a few slides. Good. So, the model structure of a generative model. In essence, a generative model can take any kind of structure. So any probabilistic sort of graphical model, you can call it a generative model. So if it uses random variables, if you can simulate from it, it's a generative model. However, there is a very common sort of structure that a lot of different very popular models in machine learning especially tend to have, and that's the structure that we're going to be talking about here. So this is not the only structure of any kind of generative model, but sort of a popular one, because generative models in general cover sort of any probabilistic model that can make use of random variables to simulate new data. So it's a very broad definition, but again, there are certain architectures or certain structures that tend to be quite popular in practice, and we'll see a couple of them. So the goal of generative models, as we said, is to generate synthetic data Y. Now, the way that commonly this is done is by assuming some latent representation called eta. Now, this is not an actual sort of observed variable. This, you can think of it as just some random noise, essentially, or some variable that's sampled from any kind of Bayes distribution. In this case, I picked it to be a univariate Gaussian, for example, and it's just a latent variable, it's called, and we're calling it eta here, and it's modeled as a random variable. Now, the next step is, or the next component of a generative model, or of this particular structure and class of generative models, is often a parametric function f, which takes input eta, so takes input this latent variable that we sampled, and either returns a probability distribution for y, given this latent variable eta, so given a specific value for eta, or it returns a single point y directly. So it either returns y directly or it returns some distribution for it, for y, from which we can then sample, basically. And so you can think of an example here is that f of eta, he returns this normal distribution. The normal distribution depends on eta because the mean of that normal distribution is a linear function of eta. So it's an affine function or a linear function of eta. And then we have some covariance matrix parameter here that's also fixed. And so as far as when you're generating data from this model, if you think about it, how would you generate data from this model? You would first sample some values for eta here, plug it in here to get the mean, and then you have the mean as a vector, so just a two-dimensional vector and the covariance matrix, and then you can sample from that distribution to get samples for y. And you can do this over and over and over again and get as many samples for y as you actually want. And so that's why it's a generative model. Now, in here, I just plugged in these values as if like I knew what the actual values were, but then in practice, obviously, you would have to actually learn what these parameters are. So learn what these coefficients here are, learn what the covariance matrix should be, such that you can actually match the distribution of the data. And we'll see how we can do that in a couple of slides. Okay, so let's maybe discuss more the latent or about the latent variables. So what is a latent variable? What should it be? What kind of constraints are usually put on it? So the idea of this latent representation or latent variable is that it should be low dimensional. It doesn't have to be, but it usually is. And it's fixed length. Now, this is a very important point because, as we said before, our data can be heterogeneous. So technically, I could have a sort of different number of points for subject 1 versus subject 2 versus subject 3. And the idea is that by having a single sort of length for eta for all subjects, or the idea is that eta should, regardless of what the dimensionality of y is, have the same dimension across all subjects. Now, that's, again, not an absolute necessity because we could define probabilistic models that even have a variable number of latent variables, and the number of latent variables could itself be a latent variable, and we can keep doing that kind of thing. But the most common structure is that eta here would be a fixed length, low dimensional representation or variable that we pick. So it's often low dimensional, it's often fixed length, again, not necessarily, but quite often it is both of these things. When I say low dimensional, I mean low dimensional compared to the dimensionality of the data. So if I have data that's made of images and the image has thousands of pixels, I could still have an eta of dimension 100, for example, and that's still considered low dimensional compared to the dimension of the data. If the data only has like 3 or 4 points per subject, then probably not many etas should be used for such a model, or not many. The dimension of eta should be roughly less than 3 or 4 as well. Good. So eta is also often modeled as a random variable, which is sampled from some distribution. Now, this distribution is called here parametric distribution because it has certain parameters. And so here the parametric distribution is just this univariate Gaussian. It has parameters mean equals 0, standard deviation equals 1. Those could technically also be trainable parameters. So these I could either fix. In this particular model, they should be fixed, but for identifiability. But you could, in other kinds of model structures, you can actually also learn the parameters of the distribution of eta. And so it's a parametric distribution, but also it's often called a prior distribution, and that's coming from the Bayesian literature. If you're sort of familiar with Bayesian inference or Bayesian concepts, in essence, this is the prior distribution on this parameter here, and the idea is that if we then observe y, we can actually get the posterior distribution of eta given y, and we'll come to that in a few slides. But it's often called the prior distribution as well. At least that's what I would like to refer to it as. Good. This variable has a few names. It goes by a few names. It's often called the latent variable. I think that's by far the most popular name for it in multiple different fields. But in machine learning more recently, people started calling these latent variables embeddings or embedding variables, especially when it has to do with images or videos or text. So there are some embedding models, for example, that OpenAI has created and released such that you can pass in text and then it creates an embedding vector for that text. And you can also call it a latent feature, or in our field, we actually like to call it a random effect. And again, that sort of tries to bring us a bit closer to this idea that generative models and nonlinear mixed effects models are about the same thing, or they have the same goal, they have the same model structures, they just use slightly different terminology. And so in our field, we like to call these random effects, essentially. Now, eta doesn't technically have to be continuous, it could be discrete. And if it is discrete, then we can refer to it as a cluster, as we've seen in the previous video, where you can define this latent variable as a discrete variable, and then you can actually solve the inverse problem and then do clustering with that. And so eta doesn't necessarily have to be continuous. It doesn't also just have to be discrete. It can be a mix of discrete and continuous random variables, essentially. Now, another very important distinction here that's it's subtle but it's quite important to think about is that there's actually a different latent variable eta for every point. And the concept of a point here is a bit general, so we need to define what is a point. And so in the case of the two-dimensional points in space, it's just every point in space has its own eta. In the case of longitudinal data, we usually have one eta per subject, essentially. And then in the case of images, we usually have one eta per image. And when I say one eta, I just mean one instance of eta, but this could be, for example, a 100-dimensional vector. And so there's a 100-dimensional vector associated with each image or with each subject or with each point if the point is sufficiently high-dimensional. However, the prior distribution for all of these etas is actually shared between all the points. Now that makes it that's where the subtle part comes in, because a lot of people would just think of this as just a single variable for all the subjects, and it has a distribution, and we're just sampling from this distribution, and therefore we get the different subjects. And that's true when you're actually simulating. There's actually no distinction between having an eta for every subject that has the same prior distribution versus having sort of a single eta and then we're just sampling a different instance for every subject. There is no distinction between these two when we're generating data. But it's very important to make this distinction and to understand that there's actually a separate parameter eta vector for each image when we're actually doing the inference problem, or what's often called inference in statistics, or when we're doing the inverse problem. And so if we're trying to figure out the eta given a specific point, then that's where sort of it's very important to understand that this is actually a separate eta vector for each subject. It's just that they all have the same prior distribution. So we upfront, before observing anything, they all given the same distribution, but they're still different variables. They're independent from one another. Good. Now, the next part is this parametric function. So that's the next component of this sort of very common structure of generative models that we discussed. And this decoder, this parametric function, is often known as a decoder in machine learning. And the parametric function, in this case, it's called f of eta. It can be probabilistic if it outputs a probability distribution, or it can be just sort of a deterministic decoder or non-probabilistic decoder. So as I said before, the function f here can either return a probability distribution for y given its latent representation, or it can return y directly. And so if it returns y directly, it's not a probabilistic decoder. If it returns a distribution for y, it is a probabilistic decoder. Now, another name for it is often a generator, essentially, because that's how you use, or that's what you use to generate data. You can also call it the data model or the error model in statistics. Those are also commonly used terminology. Now, the most important part of the decoder is that the architecture or the structure of the output of the decoder should always match the structure of the data. So if my data is time series data, then I should have the output also produce some distribution over time series data. If my output is an image, then the output of f should also be an image, and so on, or some distribution over images and over the different values of the pixels. And so that's sort of the main constraint, but otherwise f can be arbitrarily complex. I can have inside of here, this could obviously be a simple linear function, or it could be some mechanistic model that we define using differential equations. It could use neural networks, it could use neural ODEs or neural ordinary differential equations. It could have sort of arbitrarily complex structure inside of it, as long as it takes an input that's fixed length, and it returns an output that has the same structure as the data. So these are the only two constraints on what a decoder should look like. But otherwise, you're free to define it however you like. Now, let's talk a bit about the parameters. And so far we've assumed, for example, in this simple example that we took here, is that all these parameters are known ahead of time. But we're obviously not going to assume that when we're actually trying to fit or train these models. So let's talk a little bit more about the parameters. So the parameters, generally there are parameters for the decoder function, and that's where most of the parameters are going to be, most likely. And then there are some parameters for the prior distribution of eta. Now, the idea is that those parameters are actually shared between all of the points. So unlike the latent variables, we have different set of variables for each subject or for each point or for each image. The parameters here of the decoder and of the prior distribution, these are shared. So these are all shared between all the subjects. They're not sort of individualized. And that's because they're shared. They're often called population level parameters, at least in the context of hierarchical modeling and nonlinear mixed effects modeling. And so this term here, you'll see it used a lot, that we have these population level parameters. And that's to contrast them to individual parameters or subject-specific parameters, which are these latent variables here. These are often subject-specific or point-specific or image-specific, right? Or occasion-specific. They're often specific to some sort of unit of data, but that's not the whole population, right? The whole population has these other parameters called population level parameters that are shared between all the subjects. Now, in pharmacometrics and in nonlinear mixed effects models, a subset of those parameters are often called fixed effects. In the mixed effects literature, both linear and nonlinear mixed effects literature, they like to use this terminology, fixed effects. And that's often to imply or to indicate that or contrast them to random effects, and where random effects would be so you've seen random effects here. These would be modeled as random variables. Fixed effects are modeled as deterministic quantities or unknown parameters, but they're deterministic. They're not random. The true parameter values, anyways. But generally, the preferred terminology that I like to use is population level parameters, because it covers these fixed effects plus all the other parameters that are actually shared between all of the subjects, including the parameters of the prior and different parameters of the decoder as well. Now, in deep learning, some maybe different, they use different terminology, and the different terminology here is just weights or weights and biases. So whenever you have a neural network, all the parameters of a neural network are usually referred to as weights or weights and biases, and we'll see example what the weights, what's the difference between the weights or the weights, between the weights and the biases in this context. But often you will just find that people use the term weights for describing the parameters of a neural network. And so that's in the case of F here using neural networks as part of it, or as part of its structure. Okay, so let's take a few concrete, or maybe more concrete examples than what we've seen so far of what a certain decoder looks like. And so imagine we have this kind of decoder here, where eta is actually a multivariate Gaussian. That's a standard Gaussian. So it's sampled from some standard multivariate normal distribution of some dimensions. You can fix a dimension to 3, 4, 5, whatever you want. Then let's imagine that we have a neural network here that takes input eta and then outputs a vector of, let's say, dimension 10. Because let's say y is the data that we care about generating or simulating, has dimension 10. And so if we have a neural network here for the mean and another neural network for the covariance matrix, and this here can return, for example, a diagonal covariance matrix that represents all the variances of all the dimensions of y, then I can essentially sample values from y. So I can sample values from eta, from its distribution, from its prior distribution, plug it in here, and then get some mean, get some covariance matrix, and then sample values for y using this model here. Now, this very specific model, or this exact structure, is actually the decoder or the generator of a very popular class of generative machine learning models known as a variational autoencoder. Right, so we'll cover this in more details in the next few slides. But in essence, as I said, the decoder can use arbitrarily complex functions, and it can even return any kind of distribution. So it doesn't have to be a normal distribution. It could be a t distribution or a gamma distribution or a beta distribution, depending on what kind of data you're actually trying to model. If your data is between 0 and 1, that would be a beta distribution. If your data is positive, it could be log normal or gamma, etc. And it could even be discrete. If your data is actually binary, then this could be a Bernoulli distribution, for example. Right? So the decoder just needs to match the structure of the data, or the output of the decoder needs to match the structure and the constraints on your data directly. But otherwise, you have a lot of freedom in defining how to actually parameterize it. And you can use neural networks, and those neural networks themselves have parameters that you need to then fit or find good parameter values for them, and so on. Now, the latent variable in these sort of generative deep learning models, so this largely covers a lot of classes of generative deep learning models here. The latent variable is often a vector of random degrees of freedom that the neural network can use in any way that the neural network sees fit, with the main goal that it wants to generate plausible data. And so the neural network can use these latent variables eta here in any way it sees fit, as long as the output generated y when we simulate from it matches or looks very similar to the real data, right? So we're not actually assigning any meaning to these latent variables. We're just arbitrarily sort of you can do hyperparameter optimization, but let's say we just pick some number of latent variables, give it some basic distribution here, like a multivariate Gaussian, and then let the neural network do most of the heavy lifting of essentially transforming this distribution into the distribution of the data. Right? So it's a distribution transformation, essentially. It's a way to transform your distribution of etas to your distribution for y. Right? That's what this decoder here does. But again, there's usually no specific meaning assigned to these latent variables. Now, there are exceptions to that, and there is a whole field of interpretable and explainable representation. And so that there are attempts to actually try and also build some meaning into this. But that's out of scope for this presentation anyways. But in the vast majority of cases, sort of the meaning of these etas is often emergent behavior, in the sense that you train the model, then you can do some sensitivity analysis where you change the first eta and see the effect it has on y, change the second eta, see the effect it has on y, but then you're not really necessarily building in some meaning or semantics into what each eta is actually supposed to do. Although often you will find that some etas, not all of them, but some of them might end up exhibiting some very unique behavior and clearly sort of visible behavior that you can interpret. And so you might get lucky and you get some interpretable behavior for some of these random effects, but in essence there is no guarantee that you will get that in general, unless you try to explicitly build it into the model. So as we say here, what each latent variable does to y or to f of eta is most of the time emergent behavior, unless you try to explicitly build it into the model. And most of the time it's not something that's actually engineered into the model, because the main goal here is to just learn the distribution of the data regardless of what this lower dimensional representation or these latent variables actually mean. Their meaning is often of secondary importance in many of these use cases. Good. Now, to contrast generative deep learning models to what I call here generative pharmacometric models, or let's call them maybe generative mechanistic models. In generative mechanistic models, the decoder is still a function, obviously, that takes an input eta or an input latent variable that we call the random effect, and it still returns a distribution, for example, a normal distribution. The parameters of the distribution are usually described by, so when I say the parameters of the distribution, I mean, for example, the mean and the variance or the covariance matrix of the distribution for y. Usually those are described by some mechanistic model, so that's based on some differential equations, or a scientific model, so that's a PK-PD model, for example, first order absorption model with maybe a depot compartment, and so on. And so there's often a mechanistic model that's actually used inside of F here as opposed to a neural network. And that mechanistic model then tells me something about the distribution of each observation basically at each point in time. And we'll come to the time part in a few slides as well. But in essence, at a high level, the decoder in pharmacometric models is not much different from the decoders used in deep learning. It just uses a different structure inside of it, but it's still nonlinear. Both of them are nonlinear most of the time, at least, and it's just that here we use a mechanistic model that's based often on differential equations. At least that's one common case, but it's not the only time that we actually, or not the only type of models that we typically use in pharmacometrics, because sometimes we don't actually know what the mechanism is. We don't actually have a good idea of, for example, how tumor size evolves based on or given certain drug. And the mechanism, the exact relationship between tumor size and the drug is much more complicated than what we're able to model ourselves. And so often people would rely on quote-unquote empirical models, or these empirical models, which we can also call the machine learning models, are models that are really not meant to capture any specific semantics or mechanism. They're just meant to be flexible enough that they're able to fit many different kinds of relationships. So the goal is to just fit some input-output relationship. And this input-output relationship, again, we don't really have a very specific mechanism for it. But the idea is that just using the data, using some data for the input and the output, we should be able to fit some very flexible model that tells us exactly what or how the output behaves as a function of the input. And generally, these empirical models tend to be good at interpolating, but slightly worse at extrapolating. So mechanistic models tend to be, if they're well specified and well fitted and identifiable, they tend to be good at both interpolation and some level of extrapolation, not too far into the future as well, but these tend to be slightly better at extrapolation compared to full empirical models or machine learning models. And then there is a class of models that are between the two, called semi-mechanistic models conventionally, or semi-empirical models, if you like. But more recently, they've been sort of rebranded as scientific machine learning, where it combines components of scientific modeling or mechanistic modeling, like some differential equation of absorption and clearance, with some empirical component, like, for example, an empirical function for exposure response. Or an empirical function for, let's say, the survival function or the hazard function in a survival model. And so you could be combining these mechanistic and empirical components together to get some semi-mechanistic decoder, essentially. And so, as I said before, the decoder can be arbitrarily complex. It can use any kind of structure that you want, as long as the output has the same structure as the data, and the input is this latent variable that's more often than not just fixed dimensional and low dimensional. Now, in pharmacometrics, the sort of one of the main differences between pharmacometric models, or generative pharmacometric models, as I call them here, which I think you are more familiar with maybe the terminology nonlinear mixed effects model, but it's the same idea. The main difference between the latent variables or the random effects used in these generative pharmacometric models and the latent variables used in generative deep learning models is that often the latent variables used in these pharmacometric models have a specific meaning or interpretation assigned to them. And the interpretation is often that it's the subject's deviation, so an individual's deviation from the population's typical value. Now, I did mention that every individual has their own instance of eta. Right? And the interpretation of that is that this eta here is a specific individual's deviation or difference from the population typical value for some quantity of interest. So, for example, if I take here the clearance rate, which is how fast or how quickly the body is getting rid of the drug through the kidney and the liver, usually. And so the clearance here, or this parameter here, or this variable that represents clearance, I can define a typical value for it, that's a positive number, and then I can multiply it by the exponential of some random effect here that has a mean 0 and some covariance matrix, or some variance parameter, or standard deviation. So that's just a single number here. And so the idea is that if this number here is positive, is more than 0, then the exponential of that will be more than 1, and then the value of the clearance for this specific individual will be more than TVCL. So because TVCL times a number that's more than 1 is going to give me something that's more than or greater than TVCL. And so in that sense, this eta CL here represents in log scale the deviation from the typical value. How far, the higher the eta is here, if eta here is like 3 or 4, then we're multiplying TVCL by a much larger number than if eta CL is just like 0.1, for example. Then we're multiplying TVCL by a much smaller number that's still greater than 1. Now, if eta CL is negative, then the exponential of that will be less than 1, and we'll be multiplying TVCL by a number that's less than 1, giving us a clearance for this individual that's less than the typical value. All right? And so the, again, interpretation of eta CL here is that it's some deviation from the typical value in log scale, often for these parameters. And that's the main sort of distinction between the latent variables in the context of pharmacometric or mechanistic models and the latent variables in the context of these more generative deep learning and generative machine learning models, where the latent variables there tend to not have any specific meaning assigned to them upfront. Now, the typical value TVCL here would be basically one of the parameters of the decoder, right? So this here would be part of the decoder that's decoding the eta CL to produce some concentration curve over time, and TVCL here would be part of, or one of the population parameters that's part of the decoder, just like the neural network weights in generative deep learning. Often also the prior distribution of eta CL has some parameters, and those are also population level parameters. Commonly they are referred to as the omegas, or the between subject variability parameters. Those are also additional population level parameters. And so often here would have this 0, but then would have some omega here, and instead of just the identity matrix, and omega would itself be a population level parameter that needs to be fitted. And the interpretation of the prior distribution of eta, or at least of the covariance matrix of the prior on eta, is that it's the between subject variability, or it measures how much between subject variability there is that's not explained by the covariates. And so often we might have some measured covariates that explain why subjects 1 and subject 2 behave differently, for example, or have different response to the same drug dose. But then sometimes there's difference between them that's due to some unmeasured quantities, like genetics or some other factors that may not have been measured. And in essence, the latent variable here is a catch-all representation or latent representation or latent variable that's ideas that represents all these other sources of variability that we have not explicitly measured. And the covariance matrix of this eta here essentially represents if when we fit the model we find that we need an omega here that maybe is like 100 times the identity. That means that there's actually so much variability that's not really explained by any measured quantities or any covariates that I might have in the model. And we'll come to how to handle covariates again in the next few slides. But the idea here is that this omega or these parameters have an interpretation, right, in pharmacometric models, unlike or in contrast to the parameters in generative deep learning, which often don't really have a meaning. Like the weights of the first layer of a neural network, usually there's no specific meaning assigned to that. While the parameters of a pharmacometric model or a generative pharmacometric model often has specific meaning assigned to the parameters, to the latent variables, etc. Good. So now that we've seen sort of the overall structure of a very common sort of a class of generative models, both generative deep learning models, but also generative pharmacometric models, let's talk a little bit about what we can actually do with these models. Now, we said initially is that the goal of these generative models is to sample data that looks like the real data. So how do we actually sample from them? And we briefly discussed this before. Sampling from the generative model is basically a three-step process. The first step is to sample a random variable for the latent representation eta from its prior distribution. So we take this distribution here, we sample a value from that. And that gives us a specific value for eta. Then we can quote-unquote decode eta. So we can pass it through the decoder using this function here, f of eta. And the idea is that it gives us a distribution for y. Now, it could also just give us a value for y. And if it gives us a value for y, then it's just a two-step process and we can just return the value. But if it gives us a distribution, then the third step would be then to sample from this distribution to get a specific value for y. So those are exactly the three steps you need to follow to sample or to generate data from a generative model of this particular structure. And the distribution output by f of eta here is often called the conditional distribution of y given eta, right? So given a value for eta, we can define a distribution here for y. So this here is often called the conditional distribution of y given a specific value or given eta. Then there's another term that's called the marginal distribution of y. And the marginal distribution of y would be the distribution of all the sampled y values by following this process here over and over and over again, or doing these three steps here and repeating them many, many times. The values of y that you get at the end and the distribution of the values of y that you get at the end is often called the marginal distribution of y. And often the marginal distribution doesn't have a closed form, even if the conditional distribution have a very specific closed form. But the marginal distribution, at least for nonlinearity, so if this here was a nonlinear function, often it doesn't have a specific closed form for that we can just point at and be like y is a gamma distribution or y is a log normal distribution. So it doesn't have a specific name, let's say. It's still a distribution, nevertheless, though, of a bunch of values that are generated by this model, right? So again, it's important to keep this terminology in mind. This is the conditional distribution, and then the overall distribution of all the values sampled by first sampling eta, passing it through this model, through the decoder, decoding it, and then sampling y and repeating. The overall distribution is called the marginal distribution of y. So this is how we sample from a generative model. Now let's talk about how we actually fit these models, and maybe more details about fitting will come in a separate presentation later. But the idea is that we look at an intuitive level. The goal of fitting generative models is to find the best parameters for the decoder and the best parameters for the prior. And by some definition of best. And so usually the definition of best that we care about is that intuitively, again, the distribution of the real data should match the distribution of the simulated data. Now, one such measure that when we maximize actually tells us how well the real data and the simulated data align with one another is called the marginal likelihood. And so we're often interested in maximizing this marginal likelihood, or the log of the marginal likelihood. So we often do the optimization in log scale. Now the log function is monotonically increasing. So by maximizing the log of anything, I'm maximizing that thing itself, essentially, and vice versa. Right? So if I maximize this, I'm also maximizing the log of this, because the log just is an increasing function, essentially. But the idea here is that we, by maximizing this marginal likelihood, which often is also called the evidence, essentially, in Bayesian statistics, often it's referred to as the evidence, then we're actually indirectly aligning the distribution of the real data and the distribution of the simulated data. And there's actually a proof for this, and it's not included here, but maybe we'll discuss it in a future presentation. But the idea is that, like, if you're familiar with the concept of the Kale divergence or the Kullback-Leibler divergence, basically maximizing the marginal likelihood is equivalent to, asymptotically, as you have large number of points, is equivalent to minimizing this Kale divergence between the unknown true distribution of the data and between the generated distribution. So the distribution, the marginal distribution of y here, and the true data generating distribution that we don't actually know. So usually when we have some data, we don't know what the true data generating distribution is. We try to make hypotheses about that, but we generally don't know that. But in essence, the maximizing the marginal likelihood for a specific model is equivalent to try to align the distribution of simulated data from this model to the distribution of the real data that is unknown, right? And we can show the derivation maybe in a later presentation. And so this is a very common objective function value. Now let's talk about the individual terms in this objective function. So the p of yi given eta is the probability that the random variable y takes a specific value yi according to distribution f of eta. So let's break this down. So f of eta here is a normal distribution, for example. And so the probability that, for example, y takes a value of 0 would be the PDF, or the probability density function of this normal distribution for a value of y equals 0, right? And so we can just plug in the value of y in the probability density function of this distribution f of eta. And that gives us this term here, which is p of yi given eta. So we can very easily compute this, right? It's not that difficult. If you're able to actually write it down in a closed form, this often has a closed form distribution, and if you're able to write it down and define it programmatically, you should be able to also calculate its probability density function, because it often has a closed form or an easy enough to calculate probability density function. So that's easy to calculate. Now, this term here is basically the prior distribution, or the probability of eta according to its prior distribution. And so again, let's go back to this example. The prior here is a univariate Gaussian in this case. And if I have an eta of 0.1, for example, the probability that eta is equal to 0.1 is the probability density function of this standard Gaussian, or this univariate normal distribution, at eta equals 0.1. So I would just need to write down the probability density function for this distribution and then substitute eta equal to 1 to get this value here, right? Now, the idea of the marginal likelihood is actually we're taking the integral of this product here for all values of eta. So if eta here is unconstrained from minus infinity to plus infinity, excluding the infinities, like for example in this case, it's an unconstrained random variable, then we would just be integrating over all these possible values essentially. Now you can imagine that this integral might be difficult to compute. In general, actually, if you have only 1 or 2 dimensions of eta, you can actually get a pretty good approximation of this integral using something called quadrature methods. But as the dimensionality of eta increases, this integral becomes quite difficult to compute in practice. And a lot of the sort of magic of these statistical software that are used, like Pumas and DeepPumas, is essentially in just defining these algorithms and methods to try and maximize the marginal likelihood, either by approximating it first or by putting some lower bound on it and then maximizing that. And there's quite a lot of techniques that one can use to actually try to maximize this. But intuitively, let's just maybe at a high level try to understand that this here is a desirable objective function value because it corresponds to minimizing some discrepancy measure between the true distribution of the data, the observed data, and between the generated distribution or the distribution of generated data, or the marginal distribution of y. And that's why we are interested in maximizing that. Now, the n here would be the number of points or images or subjects. And so we just take the log of the marginal. So this here would be the marginal likelihood. This is the log of the marginal likelihood. And then we are interested in maximizing the sum of the log of the marginal likelihoods, which is the same as the log of the products of the marginal likelihoods as well, which is the same thing as just maximizing the product of the individual marginal likelihoods. And so again, this here is a very popular objective function value that's actually used in both pharmacometrics and in generative machine learning. So this is the exact same objective function used to fit a class of generative models called probabilistic principal component analysis, which is very closely related to a concept called factor analysis in statistics. It's also the same objective function value used to fit variational autoencoders in general. So that's again another very popular class of generative models. It's the same objective function used also to train nonlinear mixed effects models, or to fit all the nonlinear mixed effects models that we typically work with. So it's a very popular metric, and we can talk about it for a very long time, but maybe that's for another day or another presentation. Good. So we've talked about sort of 2 things we can do with a generative model. We can sample from it, and then we can fit the model. And the way we fit the model is by maximizing this. And the things that we can tweak basically are all the parameters of f and all the parameters of the prior distribution. These are all the things that we can tweak such that we can maximize this. And then we said that maximizing this is typically not that trivial, and it needs a lot of sort of computational tricks to get it working, but then it should be easy at least to manually tweak these parameters. If you have a simple enough model with a few parameters, you should be able just to manually tweak these parameters and then look at the data generated and actually align the distributions together. And that's intuitively what the optimization algorithm is also trying to do in essence. Now, the third thing we can actually do with a generative model is what I call here solving the inverse problem. And the idea is that instead of generating some synthetic data value or synthetic value for y from a random value for eta. So before, when we were generating data, we sampled eta first and then we got some synthetic y. In this case, we actually want to use the model in reverse. And what I mean by that is that I will actually give you the model, but then I will also give you an actual observed value y. So think of this as an actual observation from a clinical trial, an actual individual from a clinical trial. Or think of this as an actual image of a person or a photo of a person, maybe with some missing pixels. Maybe it's blurry or something, so it has some missing information. But the idea is that I give you a real, actual observed value y. Instead of having a sort of synthetic value y. And the idea here is that we would like to infer or figure out, essentially, which latent variable value, so which value of eta, which I'm going to denote the value here by eta star, that best represents this data point y. So intuitively, what that means is when we're generating data here, right, for every value of eta, I am getting some distribution for y, and then I'm sampling y. Now, I could ask the opposite question, is if I give you a value of y, what are all the possible and plausible values of eta that could have generated this y. So assuming this y came from the model or was generated by the model, if you assume that, what are all the possible values of eta here that could have possibly generated this y? And in particular, I'm interested, if possible, sometimes there's a unique best value of eta. If the model is quote-unquote identifiable, there's often a unique value of eta that's the most likely value to have generated this data point y. And that's what I'm denoting here by eta star, right? And so we're sort of using the model in reverse now. And the way we can actually find this eta star is by solving some optimization problem. And the optimization problem here will be minimizing some dissimilarity measure or dissimilarity function d. So you can think of it as some distance or some divergence between essentially the real data point y that I gave you, the real image, the real subject data, and between the distribution f of eta. Now, for the purpose of solving the inverse problem, the parameters of the model are fixed. And so we fix all the parameters of f, we fix all the parameters of the prior, but the only thing that's not fixed is eta itself, right? So eta itself now becomes our sort of main optimization variable. And the goal here is to figure out some dissimilarity function, and we'll discuss a very specific commonly used one in the next slide, such that the distance or the similarity between f of eta and y is sort of maximized. So I'm minimizing the dissimilarity, or in other words, I'm maximizing the similarity between these two. And so I would like to find what value of eta gives me the highest similarity between f of eta and between y, essentially. And now this whole thing is going to be denoted by a function g, which is here g of y. So y here now becomes the input, not the output anymore. Y is the input of this function, and the output is the value of eta star, which is the best value of eta that could have possibly generated this data y, assuming this data point y actually comes from the model that we have. So this here is what we call the inverse problem. Now, d could basically be any dissimilarity function, but we will discuss a very specific one that's very commonly used in mixed effects modeling. And that's here, it's the negative of the log of the joint probability. Or because, again, the log is just, like doesn't actually change it much in the semantics. It's just the, essentially 1 over the joint probability, right? That's what we're trying to minimize here. And so you can think of this as us trying to, because we're minimizing this, we're basically maximizing the plus. So if you switch the sign here to plus, we will be maximizing the positive of the log joint probability, which is the same thing as maximizing the log joint probability of y and eta. Now, this here is the conditional probability that we've seen before, which is coming from f of eta. So that's the value of, or the probability of y for a specific value of y, in this case the actual observation that I'm giving you. So the value of the probability of the specific observation y that I just gave you, given the distribution f of eta. And this distribution f of eta has all the parameters for it fixed. The only thing that's not fixed is the value of eta itself, right? And then here is the prior of eta. And the idea is that this here actually acts as a dissimilarity measure between f of eta and between y. And to take an example to try and understand why this acts as a dissimilarity, let's actually imagine that this distribution here was just a Gaussian centered around 1, for example. So it has a mean of 1 and a standard deviation of 0.1, right? So that's what the f of eta value is for a specific value of eta, let's assume. Now, if y here has a value of 10, for example, now according to this distribution that has a mean of 1 and a standard deviation of 0.1, the value of 10 is extremely, extremely unlikely. And so what that means is that this probability here will be very, very close to 0. And that means the log of a number that's very, very close to 0 will be a very large negative number. So it's large in magnitude, but it's a negative number. And then the minus of that will be just a large number that's a positive number, like a large positive number in this case. And so in essence, because this is a large positive number, it is a large positive number because the distribution f of eta and the actual observation y are quite far from each other. So it acts as a dissimilarity between distribution and y. Now, if you compare this to, for example, a case where y is close to the mean, so if y was only 1.01, for example, then the value here would be a lot further away from 0, so this would not be close to 0, and therefore the log of that would be, again, less negative, essentially, and this would be less positive. And so you would just be, like you would not have as big of a number, essentially, because the distribution f of eta and the observation y are quite similar to one another. And so the more dissimilar those two are, the larger this value is going to be, essentially. Now, you can think of this minus log of the prior or the probability of eta as some sort of regularization. So it acts as a regularizer to reduce some overfitting. So if I have maybe some sort of time series data and one of the observations is completely off, I don't want my eta to be also going all the way to like 1,000 or 1 million, just because that's the value of eta that best sort of fits the data or best represents this data. So by having this additional term here, it acts as some sort of regularization to reduce overfitting, which is especially important if I only have a few observations and perhaps a large number of random effects or a large number of latent variables. Then it becomes quite easy to just overfit those 2 or 3 observations that I have, let's say in some tumor size over time. And if I have like 3 or 4 random effects, then it becomes easy to overfit. And so the goal of this here is to just reduce the risk of overfitting, essentially, if there is indeed a large noise component or some value in y is an outlier, or there are only a few points y and a large number of random effects. Now, in the context of pharmacometrics, we often measure this kind of overfitting using a metric called epsilon shrinkage. And that's maybe slightly outside the scope, but I thought I would bring the terminology here because essentially this is a sort of measure of overfitting, is that when the shrinkage is high for the epsilon, that usually means we actually fitted the noise in the model or in the data rather than just the signal. Now, this particular choice of this similarity function, when we use it, it has a specific name, or the value of eta star has a specific name. The name of eta star here becomes the empirical Bayes estimate. And this has like the term empirical Bayes here comes from the fact that we are modeling eta as some random effect, or as a random variable, essentially. So eta here is a subject-specific parameter, as we said, or it's an individual parameter, it's per subject or per image. And then the parameters of f in general and the parameters of the prior are population level parameters. And so the idea of empirical Bayes is that we are Bayesian with respect to the random effects, but then we're still empirical with respect to, or frequentist with respect to, the population parameters, right? And that's why it's called empirical Bayes. But this whole term here is a pretty standard term that's basically used to refer to this eta star value. When we use this specific definition of the dissimilarity measure, then the value of eta star is often called empirical Bayes estimate in the nonlinear mixed effects literature. Now, in machine learning, eta star is often called embedding. So you can calculate the embedding for text data, you can calculate the embedding for image data. The only difference would be the definition of f here would be different for text versus images. And obviously the number of parameters here may be very different as well. So for large language models, for example, or large language embedding models, you would have a very high dimensional parameter vector for f here. That you would need to optimize when fitting, but when solving the inverse problem, we actually fix these parameters, and all we have to do is just find the best values of eta for a specific piece of text. And again, often for language, we actually need a very high dimensional eta here because language is quite diverse, and so often a very high dimensional embedding vector is used to represent text rather than just 2 or 3 values, for example. And so even if you have a text that's just made of one letter or one word, you can actually embed it into this high dimensional vector, in this case like a 100-dimensional vector. And so in text, for example, that's often a case where you may have, again, very varying lengths of data. So some data might be just one letter, some data might be one word, maybe one sentence, one paragraph, etc. But they all get mapped to the same length of vector of eta. right? So eta has the exact same length for all of them, whether it's a character or a word or a sentence or a full paragraph or a full page. And that's, again, very similar to pharmacometrics, where whether I have only a baseline observation or a baseline plus 1 observation or baseline plus 10 observations, they all get mapped, or they all have a set of random effects that we can always find. Like I said, like the empirical Bayes estimate has the same dimensionality regardless of the dimensionality of the data, even in pharmacometrics. And so the term embedding, if you open a machine learning paper, you'll find that it's used a lot, or embedding models is used a lot. Now, in this particular optimization, as I said before, the parameters of f and the prior distribution, which we had already fitted by maximizing the marginal likelihood, those are kept fixed. Those are not changing in this optimization. And in the specific case where the dimension of eta is less than the dimension of y. Now, I say here often less because it's not always less, as I said, with text, for example, or even with pharmacometrics, where I only have 2 observations for a specific subject because he dropped out. Then in that case, eta might not have a lower dimension than y. But often it has less than the average dimension of y, or its dimension of eta is less than the average dimension of y. And when it is less, so when the dimension of eta is actually less than the dimension of y, this inverse problem can actually be used for dimension reduction, which often also has, again, like a related sort of concept in statistics, is this so-called factor analysis, or we can call it feature extraction. And so what you can think of this as, like, let's think of this function here, right? So this function here, g of y. So if I give you a value of y that's maybe an image with 1,000 pixels, then it can return a value for eta star that only is a vector of length 10. And so I've essentially reduced the dimensionality of this 1,000 dimensional vector or data point to just 10 vector or 10 dimensional vector, right? And so you can again imagine this here being some tumor size over time, or some pK concentrations over time, and then I can reduce it to just some random effects on, for example, absorption rate, clearance rate, and volume of distribution. And so just 3 random effects or 3 empirical Bayes estimates essentially capture the essence, or capture the main sort of message or the main signal in this much higher dimensional data, which might be 10, 20, 30 observations, for example, over time. And so when the dimension of eta is less than the dimension of y, this can be used for dimension reduction. Another popular use for this is, or for the inverse problem, is that we can generate a fixed length encoding. So you can think of this as an encoder, and that's another actually name for it, is that this whole function here is basically encoding this y into some fixed dimensional or fixed length vector. Because y, as we said, the data that we usually work with is heterogeneous, and so some images might be bigger than others, have more pixels than others. Some scans might be have a higher resolution than others. Some time series might be longer than others. And yet for all of these sort of different types of data, or different sizes of data, we can actually get the same fixed length representation, or at least the same length of the representation. The actual value will be different, of course, but the length will be the same. And this is quite useful if I want to pre-process this data, for example, to use it in tabular models, or in models that don't know how to deal with this heterogeneity of the data, and don't know how to deal with the fact that, again, some subjects might have more observations than another. And so I can use this kind of model essentially to pre-process my data. So if I have image data, I can pre-process it, generate this so-called embedding vector, and then use the embedding vector just like any other covariate, do some linear regression with it, or go and do some exposure response analysis and add it as a covariate there, right? And so you can essentially use this so-called encoder to encode the variable length data that we have into a fixed length encoding, or a fixed length representation, eta star. So that's another common use of these, what I call here the inverse problem, or using the generative model but in reverse. Now, another common use is if eta is discrete, like for example in Gaussian mixture models, then the inverse problem can be used for clustering. And so if I, again, try to find, so this minimization here doesn't have to be over a continuous eta, right? So if eta is discrete, for example, it can only take values 1, 2, 3, or 4, the way to do this minimization is actually quite simple. You just substitute eta equals 1. Here, substitute eta equals 2, eta equals 3, eta equals 4, and find the minimum value at which value of eta it happens, and then that gives me eta star, whether it's 1, 2, 3, or 4, right? It can only be one of those 4 choices. And basically, you can think of this then as a clustering algorithm. So for a specific value of y, I'm finding whether it's cluster 1, or cluster 2, or cluster 3, or cluster 4 that best represents this data. This data most likely belongs to that cluster or was generated from a distribution for that specific cluster. So again, if eta is discrete, then we could actually use this, and eta is discrete and sort of categorical or nominal, then we can use this kind of algorithm for clustering. Now, solving the inverse problem, as I said, is often called encoding the data, and the model, the function that does it, is often called an encoder as well. Now, often in machine learning especially, maybe not much in pharmacometrics or nonlinear mixed effects modeling, but in machine learning, we don't want to solve this optimization over and over again. So I might have many different values of y. I might have like my data set might have 1 million images, right? And the idea is that if I have that large size of data, then fitting this optimization or solving this optimization for every specific data point and every specific image can be quite time consuming. And so it's not unpopular, it's quite popular to then go ahead and try to approximate this. Instead of actually solving the optimization, you approximate it with a neural network. So you try to use some neural network here for G, and then you try to get some approximation of what eta star is. And either you can approximate eta star, or you can approximate the distribution of all possible values of eta that could have generated y. So this could also be an entire distribution of values that we're actually trying to approximate. And so training a surrogate neural network, so the term surrogate here is used to refer to the fact that we are not doing the optimization, but we want to replace it or approximate it with some surrogate model that we can then quickly evaluate. So for a new value y, I can quickly evaluate it, and it gives me an approximation of eta star rather than the actual eta star. And so it's common in machine learning that we actually have these surrogate neural networks instead of having to do this optimization. And this surrogate model is often called the encoder, right? Although the whole optimization here can also be called an encoding, essentially. And you can think of this whole optimization-based function as an exact encoder, essentially, whereas this here would be an approximate encoder. Right, so those are the terms I'm going to use here. So whenever we have a surrogate model, it's an approximate encoder. But whenever we actually solve the optimization, assuming we converge in the optimization to the global maximum, which is not guaranteed, of course, but assuming we do converge, then that's an exact encoder, essentially. Now, of course, if we are interested in not just a single most sort of likely value eta star, but a whole distribution, then instead of doing this optimization, we would be doing something like Markov chain Monte Carlo, where we're actually sampling from the posterior. And so there is also a probabilistic version of this where we don't just get one value of eta star, but we get all the possible values of eta that could have generated the value of y. And we'll come to this in the next few slides. So as we said here, the optimization-based function is itself an exact encoder, although in machine learning, people often use the term encoder to refer to the neural network approximation of the exact optimization-based process, which is more popular or more useful when you have a lot of data. But in pharmacometrics, often we don't have that much data, and therefore it's much less popular to do this approximation, and often we just do the optimization for each subject, or do the MCMC or the Bayesian sort of sampling from the posterior for each subject. Now, as I said, the surrogate also can actually learn an approximation, not just of a unit or sort of a point estimate or a single value eta star for each subject, but it can learn a distribution of values of eta for each subject. And those are the values of eta for each subject that could have plausibly generated y. So there might not be just a single unique value. If I have only, let's say, a baseline tumor and one observation, then it's not clear yet exactly whether this maybe person will have their tumor shrink or their tumor grow over time, right? And at what point exactly they might shrink or grow. And so just from maybe very few observations, there may not be a unique value of eta that best sort of represents this data. And there might be multiple values of eta that equally well explain or that equally well could have generated these maybe two observations that we've seen. And so this concept of the distribution of eta values that could have plausibly generated y is often called the posterior distribution. And it's denoted by this symbol here. So it's the probability of eta given y. Right, so given a specific value of y, which could be a real observation, for example, two observations of tumor size, one baseline and one after baseline, given that those observations here, what are all the likely values of the latent variable or the random effect that could have explained or that could have generated these two observations for y? Now, this concept here is called the posterior distribution, or is often called the posterior distribution. And we can actually approximate this whole distribution instead of just approximating eta star using an encoder as well, a so-called probabilistic encoder, or another term for it is variational encoder. Right? So when the encoder is not just trying to approximate or figure out a single value for eta, which is eta star, but rather is trying to approximate an entire distribution, or the whole posterior distribution, it's often called a variational or probabilistic encoder. And you can think of this as like basically you would try to approximate the posterior using something like a normal distribution. So I can assume that my so-called variational family or variational distribution is a normal distribution, which is the approximation family that I picked. And then all I have to do is just pick the mean and the covariance matrix of that normal distribution that will best approximate the posterior. Now, the true posterior may not be Gaussian, and so that also introduces some approximation. And just like the surrogate neural network here, it will not give me the exact, the probabilistic encoder does not give me the exact posterior, but it gives me an approximation of the posterior. Just like here, this surrogate neural network does not give me the exact output of the optimization that we should be doing. Rather, it's giving me some approximation of it, essentially. So it's a very similar concept, but applied to the whole posterior rather than just, in essence, the mode of that posterior or a single value that best represents the data. Now, this whole concept of learning a surrogate model for the inverse problem to avoid solving it for every y, where I'm not trying to do MCMC for every subject, I'm not trying to do optimization for every subject, this whole concept is actually often called amortized inference, or sometimes called amortized learning, but I believe amortized inference is actually the more popular term. And the idea is that when we're fitting these models, actually one can do amortized inference simultaneously while fitting the model. So I may have given you the impression that we first fit the model here and then we do the inverse problem, or we solve the inverse problem, and that's quite popular as well to do. But in the context of deep learning or generative deep learning or variational autoencoders in particular, often we can actually do these simultaneously. So we can be fitting the parameters of the model while also trying to figure out what the best surrogate model is that would, let's say, fit eta star or approximate the full posterior. So we're directly trying to sort of approximate the posterior for each subject while also fitting the model at the same time. So we can train them at the same time. And so we're training the decoder or the generator together with the encoder at the same time. Good. So with all this sort of theory and background in mind, let's maybe take some very concrete examples of popular deep generative models that use the exact same concepts that we just discussed here. And so the first model we're going to take or we're going to consider is this so-called variational autoencoder model. And this one has a latent variable that's a standard Gaussian. So just let's say 3-dimensional, 4-dimensional, 10-dimensional, however many dimensions you want, but it's a standard Gaussian with mean 0 and the covariance matrix is the identity. The second component is the decoder, and the decoder of a variational autoencoder is a probabilistic decoder. What that means is it outputs a distribution of y given eta. So for every value of eta, for every value of the latent variables, it gives a distribution for y, not just y directly, not a single point y, but a whole distribution for y from which we then need to sample to generate y. And the decoder is also neural network based. In fact, it's exactly It's exactly this model that we've seen before, this here. So the decoder is neural network based, where the mean is defined by a neural network and the covariance matrix is defined by a neural network. This often has specific structure like diagonal, or could be even a fixed variance times the identity matrix. So we can impose some more structure on the covariance matrix here, but the idea is that it often has the most sort of vanilla variational autoencoder often has this kind of structure where it's a normal distribution, for example, for the output. Doesn't have to be, again, technically a variation autoencoder can have any kind of distribution, but the more common sort of architecture is with a normal distribution here, and the parameters are defined by some neural networks. Good. So going back to the previous slide on VAEs, so we said that the decoder is probabilistic, so it outputs a distribution, most commonly a normal distribution, but not necessarily, and it's neural network based, meaning the parameters of that distribution are defined by a neural network, or are the output of a neural network, and the parameters of the neural network are then the things we need to, or the parameters that we need to optimize when fitting the model. Now the encoder, which as I said is just trying to solve the inverse problem, and the encoder in variational autoencoders is approximate, meaning it uses the concept of amortized inference, where given a new, like some value y, we're trying to learn a function that gives us a distribution for that approximates the posterior of eta given y, right? So what are all the plausible values of eta that could have generated y? When we try to approximate that with some closed form distribution like a Gaussian distribution, this is an approximate encoding essentially. And so in variation autoencoders, the encoder is an approximate encoder. It's probabilistic in the sense that it's not just trying to approximate eta star, which is just a single value of eta, but it's trying to approximate the full posterior of the full posterior distribution of eta given y. And so it's approximate, it's probabilistic, and it's also neural network based. And so this function here, the function that tries to approximate, or the function g here, that essentially tries to approximate the normal distribution or some distribution that approximates the posterior, is using neural networks. So the function g uses some neural networks to define, let's say, the mean and the covariance matrix of the Gaussian approximation of the posterior. Right, so whatever approximation family we pick, the parameters of that are often defined or parameterized by neural networks themselves. So it uses the neural network for the decoder, it uses a neural network for the encoder. It's probabilistic in both, and it's approximate in the encoder, and it uses the standard Gaussian latent variable. And that's precisely what the sort of original variational autoencoder model was, or still is, essentially. Now, of course, the structure of the decoder itself, how many layers of the neural network, does it use a neural network or maybe some neural ODE? Sort of you can do different plays or different variants of a VAE that more or less maintain the overall structure, but can change the internal structure of the decoder and the internal structure of the encoder. So the specifics can be different from one case to another, The variational autoencoder is mostly characterized by these properties here. Now, another very common class of generative deep learning models, or deep generative models, is so-called a normalizing flow. And normalizing flows have very interesting applications in pharmacometrics as well, that we have some nice talk about on our YouTube channel. If you go check out a talk by my colleague Lorenzo Contento. But in essence, in this context, we're just trying to study them as just generative machine learning models. And the way that they work, the way normalizing flow works, is using, again, a standard Gaussian latent variable. The only difference, or the main difference, between a normalizing flow and a variation autoencoder is that the decoder function is not probabilistic, but deterministic. Even more importantly is that often the decoder is an invertible function. So it's a function I can easily invert. I can evaluate sort of the function or the output as a function of the input, but I can also invert it, and for a given output evaluate the input that would have generated this output. And there's a unique one-to-one mapping between every input and every output. And so the function here in the decoder is deterministic, so it outputs y directly rather than a distribution for y. And it's invertible, so for every eta there is one y, for every y there is one eta. Now this necessarily means that we have the same dimension of eta and y in this particular model. There are extensions to the normalizing flow that allow a higher dimension for the output than the input, while still sort of generalizing the theory of the original normalizing flow. But the most vanilla normalizing flow assumes that the input and the output have the same dimension. And despite being an invertible function, there's actually a class of neural networks or functions based on neural networks that can still be invertible. And so often it still uses a neural network while maintaining this invertibility or inversion or so-called bijective property, essentially. Good. Now, the encoder in the normalizing flow is usually implicit. So we think of the encoder here is, again, as sort of the inverse of the decoder. So it's actually exact. We don't need to approximate it. And it's deterministic. Again, for every y, there is a very specific value, eta star, and not a whole distribution of eta. And it's actually the inverse of the decoder. So for every value y, I can just invert the decoder and then get the value eta that's corresponding to that value y, right? So you can think of the encoder as basically an exact deterministic encoder that's actually defined as the inverse of the function that we used here in the decoder. And that here becomes a normalizing flow. Now, the nice thing about normalizing flows is if you define them like this, you can actually evaluate the log likelihood of some value y. So if I tell you what's the probability of y equals 1 or y equals 2 given this generative model, there is sort of a nice tractable way to calculate that. And that makes them really nice to use in that they're quite flexible. But at the same time, you can plug them in or use them in many of the contexts that you can use a normal distribution, or you can use a standard beta or gamma distribution. And so they're quite easy to use in any context where you would normally use a simple distribution with a closed form for the probability density function. Now, in generative models, usually like in a variation autoencoder, if I give you a value y equals 1 and I ask you what's the probability according to the marginal distribution, not the conditional distribution, according to the marginal distribution, what is the probability that y equals 1? This generally is much more complicated to compute, and it requires essentially solving this integral here that we've seen to be able to compute that. Because we have these latent variables, eta, and so on. And so it's not very trivial to compute that probability. And so it's a lot more difficult to use a variational autoencoder or the generator part or the decoder part here in place of any normal distribution or any gamma distribution. But with a normalizing flow, by defining it like this, we actually make it easy to evaluate the log PDF or the probability density function. And therefore, it becomes easy to use this distribution in any context where a normal distribution would be used. And so that's really the power of these normalizing flows here. Good. Now we've seen generative models, so let's discuss conditional generative models next, where now the goal is to not just generate data, sort of like standalone data, but to generate data based on some input or some condition. And so, for example, I can generate images for males versus images for females. I can tell you what exact gender, for example, I would like you to generate this data for. Or I could tell you which time point. So the input could be, or the condition could be time. So I can tell you which time point I would like you to generate data for. And maybe I wanted to generate data for multiple time points, time 0, time 1, time 2, time 3, etc. Right? And so, or I could tell you which age to generate images for example. And so this idea of conditional generative models is basically the idea of using covariates. And so we'll talk more about that. Now, there are different types of covariates that one could use. Generally, in pharmacometrics, we have this concept of baseline covariates, and these are covariates that are measured sort of once upfront at time t equals 0 for time series or for longitudinal data, and then they're assumed to not really change, or at least we don't measure them again, and we just use this baseline or covariate value at baseline to make some prediction about the future. And so these baseline covariates could just be input. Often it's just a tabular data, so it's just a vector, let's say, of 5 covariates for each subject. And so in essence, what we do is just modify the decoder. So the latent variable distribution doesn't need to change, but we can modify the decoder function f to now accept not just the input eta coming from this distribution, but also to accept another input, which is the set of covariates that we want to condition on. And again, so this could be a vector of length 1, 2, 3, 4, 5, whatever we want. And for example, in computer vision, this could be things like the age of the person that we want to generate an image for, the gender of the person that we want to generate an image for. It could be something like the style of the image. We want it maybe more animation style, or like a realistic sort of photorealistic image. And so this could be any sort of covariate or condition that we have used while training the data. So very importantly is that this needs to be available both when training the model, when fitting the model, but also when using the model. You need to actually define these values here. Now, XB or X baseline here could also be an image or a scan or one of its embeddings. So you can use another generative model, for example, to pre-process an image and then solve the inverse problem, get the embedding of that image, which is a fixed length representation, like maybe a vector of length 20 or 30, and then plug that in here as a covariate, right? So the baseline covariate could be coming in from another sort of pre-processor of the data that we may define as well. But in essence, the only difference is between a generative model and a conditional generative model is that we have an additional set of inputs here that represent the condition or the conditions, or more commonly in pharmacometrics and statistics, we call them the covariates or the predictors in our model. Now, we can also treat time as essentially a special covariate, where we might be able to generate, or we might be interested in generating the value of y at different time points. And so we can define here a function y of t that's basically the decoder after fixing eta, fixing xb for another input t. So for every, so these would be fixed, these are not time dependent, but then as we change the time, we might get a different value y, or a different distribution for y actually, and then we can sample from that. And so you can think of time as just a special covariate, and then often we're interested in, let's say, generating data at time 0, 1, 2, 3, 4, 5, and so we can generate first at time 0, then time 1, then 2, then 3, then 4, then 5, right? And so we just evaluate this model multiple times to get the distribution for y at these different time points, and then sample from those distributions to get an actual observation for y at these different time points. So time is kind of a special covariate like this. Now you can also have like spatial coordinates here. So if it's a scan data, you can have x coordinate, y coordinate, z coordinate, for example. And if it's a video, then you could also have like spatial coordinates and also time. And so you could more generally have here both spatial and time, spatial coordinates and time as inputs in this model. Now, another common class of covariates that we often use in pharmacometrics and in nonlinear mixed effects modeling is this concept of time-varying covariates. And those are covariates that change over time. But so it's a function of time, but we treat it as a constant function of time. We're not interested in actually fitting this or training this, and often it's just some interpolation between some measurements. So I can take a measurement at time 0 and at time 5 and at time 10, and I can do some sort of interpolation between these. It could be just a constant piecewise interpolation, like a step function, or it could be linear interpolation or any kind of interpolation that I want. But the idea is that we treat it as a continuous function of time after the interpolation has been done, and then it just becomes another input here that's actually not trained, it's just evaluated directly using this function of time. And again, you can think of this as a time-varying also image or a time-varying embedding. So if I have a bunch of images or a bunch of scans over time, I can pre-process each image and each scan to an embedding vector, and then I can have the evolution of this image in the embedding space. So I can have the embedding vector at time 0, embedding vector at time 5, embedding vector at time 10, and then I can do some interpolation as well, and then treat this as a time-varying covariate of images, or of the embeddings of images. So you could really get creative with the definitions of these conditions or covariates. Now, in pharmacometrics, maybe to conclude, I would like to include an example on a generative pharmacometric model, and hopefully this should really drive home the idea that nonlinear mixed effects models that we use in pharmacometrics, those PK/PD models, the population PK/PD models that we're used to, they are really fundamentally just generative models, right? They're the same thing as generative models used in machine learning, and in fact they have very, very similar structure and a lot more similarities than differences. So in a one compartment PK model, we often have these three random effects, one for the absorption rate, one for the elimination rate, and one for the volume of distribution, and we give each random effect here a prior distribution. So these here are the latent variables. We often call them random effects, but we can also call them latent variables, and we give it a prior distribution. The only difference between this and the sort of variation autoencoder, for example, is that the prior here has an additional parameter, which we can just fit. And actually, if you reparameterize your model a bit, you can also make this sort of have a standard deviation of 1 and then just multiply it by omega as part of the decoder. So it's not it's not strictly necessary that you have to actually have this omega here. You could just multiply it by eta, by a standard Gaussian eta as part of the decoder and achieve the same effect. But more commonly, we write it like this, where we have some omega, some variance parameter omega square here for each random effect that we need to optimize. And those are population level parameters that we optimize when fitting the generative model. And then we fix when simulating or when solving the inverse problem. So these are the latent variables of a one compartment PK model. Now the decoder would look something like this, where we combine the typical value of absorption rate, the typical value of elimination rate, and the typical value of the volume of distribution with the random effects here, which have the interpretation of the deviation or the difference from the typical value and log scale. And so we combine these together to get the individual absorption rate, individual elimination rate, and individual volume distribution. And then we use this closed form analytic solution for the one compartment PK model, where D here is the dose. So let's assume it's like an initial bolus dose given at time 0. And then these are all the parameters that we just defined from before. And then we have time here. So this is a function of time that's actually the closed form solution of an ordinary differential equation. Now we could just define an ODE and also solve the ODE using numerical integration methods or numerical ODE solvers. But here, for simplicity, I'm just defining the closed form solution. But commonly, you would have some sort of ODE as well, or some sort of ODE that you can solve. And this actually is the analytic solution to a specific ODE for this one compartment PK model. And then once we have this function C of t, basically our decoder becomes this normal distribution with mean C of t and variance sigma square. And sigma square here is a population parameter. So there's a few population parameters that we defined here. There's sigma square, there's Ka here, which is the typical value of absorption rate. There's Ke, which is a typical value of elimination rate, and there's Vd, which is a typical value of the volume of distribution. So those are all additional population parameters on top of the omegas that we need to optimize. Commonly, these would be called the omegas, and these would be called thetas, and these would be called the sigma, or this is just the sigma in standard nonlinear mixed effects terminology. But they're all essentially just population level parameters that we need to optimize. So that's a conditional generative model. That's also a one compartment PK model. That's also a nonlinear mixed or pop PK model. That's also a nonlinear mixed effects model, right? So these are all, there's also hierarchical models. So these are all the concepts that refer to this particular model structure. So the decoder here is just to define these different quantities. C of t is the drug concentration over time, or the predicted drug concentration over time. D is the dose administered at time 0. These here are the absorption, elimination rates, and volume with the random effects taken into account. So that's after applying the random effects to the typical values. And this here would be the observed response, the actual observation at a specific point time t. And this would be the variance parameter, which is actually shared for all the time points and shared for all the subjects as well. It's a population level parameter. And these are the population level parameters introduced in this model, right? But other than the structure being different, fundamentally it is no different from a model that looks like this, right? It is fundamentally the same kind of model structure, like at a high level, at a higher level of abstraction. It is fundamentally just a function f of eta, some covariates like dose, for example, in our case would be a covariate, and then time. right? And then it describes the distribution for y at a specific point in time, and then we can evaluate this or sample from this model, from this conditional generative model, at different points in time and even different doses and so on. So different values of xp, and we can generate some synthetic data. So if I'm trying to generate some synthetic population for a visual predictive check, the way I would do it is first I sample from the latent variables using their prior distribution, and then I pass the values of eta A, eta E, and eta V here into the decoder. I get a distribution of y for all the time points that I'm interested in, and then I sample from that distribution, and then I get a simulated observation or simulated response over time. And then I can compare the distribution of simulated responses over time to the distribution of the actual observations over time in my visual predictive check, right? And so the process of sampling from a nonlinear mixed effects model or from a POP-PK, population PK model, is identical to the process of sampling from any kind of conditional generative model, essentially. And again, the sort of more standard or one of the standard diagnostics in pharmacometrics is this visual predictive check, which commonly would be used to compare 3 quantiles for the distribution of the real data and distribution of simulated data. They would be the 10th percentile, 50th percentile, and 90th percentile. More commonly. I think I mistakenly said 5th and 50th and 95th before, but obviously you can change these if you want. But I believe those are the most common 3 quantiles used. And so again, the way we actually compute the VPC is by doing multiple simulations. In each simulation we get some quantile, or we get some distributions. If I have an observed population of size 100 subjects, then I simulate 100 subjects, and then for the observed 100 subjects I get the quantiles. So I do some quantile regression to get the upper quantile and the median and the lower quantile, and that's the black lines here. And then for the simulated subjects that we have, which is like 100 subjects, again same size but simulated, I can do the same process, use quantile regression to get the upper quantile, the median, and the lower quantile, and then I can repeat this simulation multiple times. And so when I repeat this, let's say 1,000 times, I will get 1,000 upper quantiles, 1,000 medians, and 1,000 lower quantiles. And the gray bands here represent essentially the 95% confidence interval or prediction interval of those percentiles or of those simulated quantiles. And the blue line is the median of those simulated quantiles, right? So the whole process for plotting a VPC is quite involved, and there are details around the quantile regression and how you want to do smoothing and so on, because often we might have different observation, different time points for different subjects, and so to make them easy to compare, we often do some smoothing or binning as well. So there's a lot more details to a VPC, but at a high level, it is just doing a comparison between the quantiles of the simulation or the distribution of simulated data and the distribution of observed data. And the goal is to hopefully make sure that they are as aligned as possible. And if there's any misalignment like this, where the black line is coming out, and it's quite improbable according to the distribution of the simulated data, then that indicates that our model is not able to capture the actual distribution of the observation, at least at those time points. So at these early time points here we have a problem, and at this time point equal 30 we also have potentially a problem. And so again, that's at a high level what a VPC is trying to actually achieve. And that's the end of this very long unit on generative models and conditional generative models and the relationship of generative models to nonlinear mixed effects models and pharmacometrics and population models that we commonly use. In the next part of the slide and the last part of the slide, we'll discuss some more sort of lower level implementation details of neural networks and trying to understand what is a neural network, what are the main components of a neural network, and sort of get more into the details. So we've sort of discussed things at a high level so far to at least set the background and set the scene, so that you understand that, okay, these classes of models that we're dealing with are actually not very different from the things you've already been working with. If you've been working in pharmacometrics or if you've been working with population models, then generative models are not really that big of a stretch or that big of a jump from what you've been working on already. And now that we've sort of established this, we will go into the more detailed concepts of deep learning and trying to really understand what a neural network is and how to define one and so on. Thank you for your attention.